In this problem, we are asked to use the pointing vector to find the power carried by a coaxial cable, where the coaxial cable is going to carry a current I. We'll say that it's carrying the current up along the inner conductor and then down back along the outer conductor, and it's carrying the current I along both of them, and that there's a potential difference between the two conductors here, V. Furthermore, we'll say the potential difference, just for ease, is set up so that we have a minus sign so that the inner is at a lower potential and the outer is at the higher potential. And that's how we'll set that up. So to start out, it says use the pointing vector, so I'm going to write down the pointing vector. The pointing vector is 1 over mu naught E cross B, and so I need to find the electric and magnetic fields in this system for the coaxial cable that I have set up. For the electric field, that's not too bad. This is a cylindrically symmetric system, and so redrawing, I've got a little charged cylinder here. If I choose a cylindrically symmetric Gaussian surface of length L, let's say, and distance S, then I can set up the problem. The Gauss's law problem gives me that the surface integral d2x in hat dot E is equal to the charge enclosed with an epsilon naught in there. So the charge enclosed is easy. It's just going to be whatever the linear charge density lambda is, and times that length. So that side is going to be lambda times little l, or epsilon naught. This side is not bad as well. Because of the symmetry, we know that the E field, okay, because of symmetry, due to symmetry, the E field, vector-wise, points only in the S direction and depends only on S, like that. N hat along the surface is going to point in the positive S direction, so that E dot N is simply ES of S. And this integral d2x will just be the surface area of the outside of this cylinder. That's 2 pi times the radius, which is S, times the length, which is L. Solving these for E gives us lambda over 2 pi epsilon naught times S, which is what we knew to be true anyways, and then we put it back into vector form. We get the electric field E is going to be equal to lambda over 2 pi epsilon naught 1 over S times S hat, like that. And so that's the electric field. But we still don't know lambda. So let's go and let's find lambda really quick. To find lambda, we will use the definition of potential. And to do that, we know that the potential difference between 2 points is equal to the integral between those points, dl dot the electric field with a minus sign. And so that's what we're going to do. We're going to plug that in, and we are going to say that we're going to plug in E. And so this gives us that the potential V is equal to minus lambda over 2 pi epsilon naught. And then the integral from A to B, if the little one has radius A and the outer one has radius B, of ds over S, which of course gives log of B over A. We can flip this around to solve for the lambda. So the lambda then is going to be equal to minus 2 pi epsilon naught times V over the log b over a over the log of this ratio. The minus sign there indicates that we have a minus on the inside, just like we wanted. And cool, so we are pretty much done with that. So now we can get rewrite our electric field, replacing this lambda. This is the 2 pi epsilon naughts are going to cancel out, so this is going to be minus v over log of v over a 1 over s hat. And so now we have the electric field in terms of what's given to us, the potential difference v. We want to go on and find the magnetic field. Okay. To do the magnetic field, we're going to use Ampere's law. Again, this is not, we have a nice symmetric system here. And so there's my Amperian loop. That's my surface. And there's the direction I'll take my loop. And the Ampere's law is written in integral dl dot b is equal to mu naught times I enclosed. Well, the I enclosed for us is just I. It's the current that's being carried. And then because of symmetry, okay, again, because of symmetry, we are going to say that the B field is going to point only in the phi direction as a function of s, like that. And the dl for s is going to be s d phi. dl is s d phi. We go ahead and do that, and we are going to get 2 pi, that's from the integral over phi, s, that's from that s, times the B field, b phi is a function of s, equal to mu naught I. And so solving for b, we get b phi as a function of s is equal to mu naught I over 2 pi s. Or if we put this back into vector notation, mu naught I over 2 pi 1 over s phi hat. And that is the B field. I'm going to rewrite down the E field from above. The electric field is minus V over log of B over A 1 over s hat. Now our final task is to use the pointing vector right here. So let me recopy that. S is 1 over mu naught E cross B to find the power carried along with in the E and M field for this wire. And so now we just need to plug this in and take the cross product, and we get the pointing vector. So the pointing vector is going to be 1 over mu naught. That'll cancel the mu naught. We're going to get a V and an I. So we get I of V, get 1 over 2 pi, this ratio, log of the ratio of the radii, and 1 over s squared. Then we are going to have minus s hat cross phi hat. To do this, I'm going to use right hand rule. S hat will point, or minus s hat is going to point in. Phi hat is going to point along the direction. If I'm correct, yeah, minus s hat points in, phi hat points along the direction. And so this is going to give us minus z hat. Okay. So that's S. The request though is to use the pointing vector to find the power. And to do that, we use the definition of power is the surface integral d2x n hat dot s. And so the surface that we'll look at will be a surface perpendicular this annulus in between these two regions, because that's the only place where these fields exist. The fields are zero elsewhere. I didn't mention that, but that's true. And so we're going to integrate over that annulus And we might as well say that the n hat will point in the plus direction if we want to go up, but we know, yeah, we'll say it's in the plus direction for now. So we'll say that the n hat is equal to the plus z hat direction, and our d2x, our integral d2x, is going to be an integral from 0 to 2 pi of d phi, and an integral from a to b of s ds. So, plugging those in, we get the power then is going to be the 2 pi, the integral over d phi is going to cancel the 2 pi. So IV times this ratio of the logs, b over a. And we get a minus sign from the minus z hat dot z hat, so this gives us a minus sign. And we get then integral from a to b, 1 over s squared s ds, which is ds over s, a to b, which is, will cancel this log of b over a. So this is going to give us the power carried. I don't know why I had a vector there. There's no vector left over. The power carried is going to be equal to minus IV, or it's being carried down. Minus sign means power's going down. And let's think about that for a moment. And so I'm going to get my picture up here again. And so it says the power's going down, and I've got a potential difference such that the outside is at a higher potential than the inside. That means that somewhere down here in the bottom there has to be a resistor to give us that potential difference. And since the resistor's down below, we know that the power has to be going down. And so that makes sense. And that is the problem. Thank you.